luck, students. Here in 5.6, we put it all together with a summary of curve sketching. And our main goal here is to analyze and sketch the graph of a function using everything we've looked at so far. So, here's just some of the review of some of the things we've looked at over the year. X and Y intercepts. Remember, X intercepts, set Y equal to 0. To find Y intercepts, set X equal to 0. Symmetry with our even and odd ideas. Domain and range. What can restrict the domain? You can't take the square root of a negative. You can't divide by 0. Continuity. Remember, all polynomial functions are continuous. Vertical asymptotes. That's where the denominator equals 0. Differentiability. Relative extrema. And remember how we find those? By looking at the endpoints of the interval and also at all the critical numbers. Concavity we just talked about, and we use that in determining if we have points of inflection or not. Horizontal asymptotes, infinite limits, and infinity. And here's the sections. You can find them in the book if you need to review on any of those. So in analyzing the graph of the function, we're going to look for domain and range and determine the intercepts, asymptotes, and symmetry of the graph. And locate the values at which f prime of x and f double prime, the first and second derivative, either 0 or do not exist. So, it's been a long phase that you started in Algebra 2 when you first started graphing polynomial functions. Remember that? When you first looked at polynomial functions, you'd plot the roots, you'd plot the x-intercepts and snake through those. So you look for where is f of x equal to 0. This gives the roots. Now that you've got the derivative, you look for where the derivative equals 0 or undefined. This gives the relative max and mins. And now we also look at where the second derivative equals 0 because that can give you your inflection points, IPs, inflection points. Now we also looked at, when we looked at rational functions, this whole idea of vertical asymptote, where f of x is undefined, that created from division by 0. And that was a key point in graphing polynomials before. Now that we have the derivative, where the derivative is undefined, or where the second derivative is undefined, we have to consider those as critical numbers that we should look at. So let's sketch the graph of this rational function. Analyze and sketch the graph of fx equals 2 times x squared minus 9 or x squared minus 4. So one of the main tools here, we can look for, here's a list of everything we're supposed to check out. The first and second derivative, x and y intercepts, vertical asymptotes, horizontal asymptotes, critical numbers, possible points of inflection, domain, symmetry, and test intervals. Let's do this first one by hand, and then we'll look at how you can do it on the calculator as well. The first derivative, we go through the quotient rule, bottom, times the derivative of the top, which is going to be twice 2x, minus the top, twice x squared minus 9, times the derivative of the bottom, which is 2x, all over the bottom squared. So it looks like we've got a 4x we can factor with x squared minus 4, x squared minus 4, minus, we take the 4x out of this, quantity x squared minus 9, all over x squared minus 4 squared. And so we get 4x times, the x squareds cancel out, minus 4 plus 9 is 5, all over x squared minus 4 squared. And we get 20x over x squared minus 4 squared. There's our first derivative, 20x over x squared minus 4 squared. That was a lot of work. I'm going to let you do the second derivative here, and the first derivative for that matter too on the TI-89. On the TI-89, to do the second derivative, we can just say d 2 left parentheses x raised to the 2 minus 9 right parentheses divided by left parentheses x raised to the 2 minus 4 right parentheses comma x comma 2 to indicate the second derivative. And that should help us come up with the second derivative quickly. And you end up with negative 20 times 3x squared plus 4 over x squared minus 4 to the third. Okay? Now let's look for some of these other things. Remember, to find the x-intercepts, we set y equal to 0. In this case, set the numerator 2 times x squared minus 9 equal to 0. And that gives you plus or minus 3 for the x-intercepts. For the y-intercept, set x equal to 0. And when you do that, you just get negative 9 over negative 4, 9/4 times 2, so it's 9/2, 4.5. Vertical asymptotes are where the denominator equals 0. So that's going to be plus or minus 2. Horizontal asymptotes, since we have the same degree, it's going to be the ratio of the leading coefficients, so it's going to be 2 over 1. So we have y equals 1 for horizontal asymptotes. Critical number is where the derivative is 0 undefined. So we've got 2 and negative 2, because those make the denominator equal to 0, and also 0 because it makes the numerator equal to 0. That'll make the whole first derivative equal to 0. Now, these critical numbers, these plus or minus 2, are not actually in the domain of the function, so we can actually eliminate those as critical numbers. We're still going to want to look at them, but they can't possibly be vertical relative max or mins because the function is not defined at 2 and negative 2. Possible points of inflection is where the second derivative equals 0 or undefined. Well, we consider plus or minus 2 again, but again, the function's undefined there. Can we make the top of the 0 3x squared plus 4? No. Because x squared is positive times 3 plus 4, that's all positive, and this makes it all negative. It can't equal exactly 0. So there's no possible points of inflection. The domain restriction is x cannot equal 2 and x cannot equal negative 2 because of our vertical asymptotes. Any kind of symmetries? Yes. We've got even symmetry because f of negative x equals f of x. Got to look out for that. That's going to make our graph look very symmetrical over the y-axis. And so our test intervals. You want to test where the function's undefined and also the critical numbers. So we want to go, we're going to break it up into negative 2, 0, and 2. Those are all the key things. Look at your critical number list, look at your gaps in the domain, and we want to test everything that goes in between there. So let's see how we did here. Delete that page. And how'd we do? Yep, there's our derivatives. Yep. Everything's hunky-dory. Y equals 2. Oh, yep. That's correct. Y equals 2. 2 over 1 is 2. Critical number at 0. There are no possible points of inflection. All real numbers except plus or minus 2. And even symmetry with respect to the y-axis. And here's our intervals. Negative 2, 0, and 2. So we want to do, seeing how negative 2, 0, and 2, see how the critical numbers are the gaps of the intervals you want to look at. And that's how you set up your chart. And you want to test points in each one of these sections to see what goes on. Now notice how this is filled out. Negative 2 and 2 make the function undefined, the derivative undefined, and the second derivative undefined. And we got a vertical asymptote there. At x equals 0, f of x is 9/2. You can put 0 in there. We determine that as the y-intercept. And f prime of x is 0. And the second derivative is positive. If you put 0 into here, you actually get negative 4 cubed. That's negative 64, negative 20 times 4, so it's negative, negative, positive. Notice I just focus on the sign of the second derivative here. And that means it must be concave up. So this is a relative min. That's the second derivative test. We could also use the first derivative test by looking at either side of what's going on with this critical number. The derivative changes from negative to positive. So the original function is decreasing, then increasing, so it must be a relative min. And here's some concavity. Let's see how this all ties into the graph. Here's somebody doing it on their calculator. Here's an example of a technological pitfall where these are two very similar looking functions, but if you zoom in, you'll see that there's something funny going on there at 20 and 21. Oh, so let's finish our sketch here. Let's make some room for the sketch. Our critical numbers were 0 and 2. That was a vertical asymptote. Negative 2, another vertical asymptote. 0, 9/2, 0, 4 1/2. That's going to be a relative min. And we've got a horizontal asymptote. Let's incorporate that too. The horizontal asymptote was at y equals 2. And we head up from there. There's that concave up section between -2 and +2. It's always concave up. Concave down in these other endpoints here. And we also have intercepts. Let's get our intercepts on there. I think they're at 3, right? Yeah, -3, 0, and 3, 0. And there we go. And that's what bears out on the sketch, on the calculator. Let's try another one. Analyze and sketch the graph of this one. F of x equals x squared minus 2x plus 4 over x minus 2. Now this time I'm going to go ahead and take a look at the first and second derivative right away in the calculator, because that can be a lot of work. Let's again review how to do this on the calculator, on the TI-89 for your first derivative. Left parentheses x squared minus 2x plus 4, right parentheses divided by left parentheses x minus 2, right parentheses comma x. That gives you your first derivative. And we get x. And for the first derivative then we get f prime of x equals x times x minus 4 over x minus 2 squared. So right away that's going to lead us to our critical numbers. We're going to have critical numbers at 0 and 4 because they make the numerator equal to 0, and also 2 because it makes the denominator equal to 0, which will make the whole derivative undefined. Okay? Then all you have to do to find the second derivative is just copy what you had before and put in a 2 after this. So take all this from before and just add that extra comma 2. And you get your second derivative, which ends up being 8 over x minus 2 cubed. I encourage you to do this with your 89s because the bulk of the work on this is analyzing the derivative. And you can easily spend 15 minutes just coming up with some of these derivatives. So the second derivative is 8 over x minus 2 quantity squared. So that also, 2, is going to be another critical number. It's a possible inflection point, but no, it can't be because it's going to make the function undefined. So actually I'm going to throw out 2 as a critical number because I realize in the original function it makes the function undefined. So we just have to look at 0 and 4 there. We're still going to lose that as some of our intervals. And also we want to look at some other things here. The x-intercepts. These are the things that are going to make the numerator equal to 0 of the original function. And this one, I believe, it doesn't have any x-intercepts, because when you set the numerator x squared minus 2x plus 4 equal to 0, you get x squared minus 2x plus 1 equals negative 3, x plus 1, x minus 1 squared equals negative 3. These are imaginary answers. You could detect that with b squared minus 4ac. So there are no x-intercepts. The y-intercepts set x equal to 0, and you get 4 over negative 2, which is negative 2. So you do get a y-intercept there. Vertical asymptotes at x equals 2. That makes the denominator equal to 0. Horizontal asymptote is the ratio of leading coefficients. Oh, but look at this. Second degree over first degree. So there are none. We do have a slant asymptote, though, and we can figure that out right away with our division. That is, for the slant asymptote, you use a little scratch work paper over here. We take our x squared minus 2x plus 4 divided by x minus 2 is define the slant asymptote now. So let's use synthetic 2, 1, negative 2, 4. Bring down the 1, multiply by 2, 0, 0, 4. So you get y equals x plus 4 over x minus 2. So the slant asymptote is just y equals x. So we do get a slant asymptote there. End behavior, which we're going to look at when we don't get a horizontal asymptote, as in this case, the end behavior, it's going to act like the slant asymptote. So it's going to go basically like that. And it might do some strange things in between, but on the left it's going to go down, the right it's going to go up just like a line with a positive slope. Possible points of inflection, can the second derivative equal 0? No, it can be undefined, but that's where the original function is undefined too, so none there. The domain, just x cannot equal 2. That restricts the domain over here. Test intervals, then, we're very much concerned with 2, and our critical is 0 and 4. So 0, 2, and 4. And we're going to want to look at the stuff in between each of those. Okay? So the stuff to the left of 0, between 0 and 2, and between 2 and 4, and beyond 4. Let's see how we did. All right, I want to look at this and delete this page. And our derivatives are all set here. Y-intercept, x equals 2, none. There's that end behavior. As x goes to negative infinity, we head down to negative infinity. As x goes to positive infinity, we head up to positive infinity from the y's. 0 and 4 for our critical numbers. No possible inflection points. Domain x cannot equal 2, and those are all the things we want to look at. So you're testing points here. You're reiterating what happened at 0, 2, and 4. 2 makes the function undefined. It's a vertical asymptote. X equals 0. We get f of x equals negative 2. The derivative is 0. The second derivative is negative. And so the second derivative test tells us then this is concave down right here, so it must be a max. We can also look at the first derivative test on either side here. Over here at x equals 4, 6, if x equals 6, when you put 4 into the original function, the derivative is 0. The second derivative, you put 6 in here, is positive. So the second derivative being positive means the function's concave up. Concave up, so you must have relative min. That's the second derivative test. You could also look at the first derivative on either side to see that it goes from negative to positive, means the function goes from decreasing to increasing. Makes a relative min. Yeah, and there's our picture. There's our relative max at 0, negative 2. Min at 4, 6. Vertical asymptote there. Oh, God. Phones are ringing. Okay, here we go. All right, and notice what's not in here is the slant asymptote that we talked about. Let's pop that in there. Got this nice slant asymptote at y equals x, I believe. Yeah. Was it x? Let's check that. Slant asymptote, y equals x, yeah. So it's more the end behavior there. Oh, they did put it in. Okay. Now, here's a little tip. If you're going to do this by hand, if you rewrite it using long division, it can help you see the slant asymptote. And it might also be easier to do the derivative of this. Check this out. F prime of x then is just 1 plus, and I'm going to use the chain rule, 4 times negative 1 x minus 2 to the negative 2, and then the derivative of the inner function is just 1. So our first derivative is 1 minus 4 x minus 2 to the negative 2, which makes the second derivative easier to do than 2. And you get 0 minus plus 8 times x minus 2 to the negative 3. So just a thought. Now we've got a radical function here. Analyze and sketch the graph of this mess. Oh my gosh. Well, let's look at some of our details. First, I've already put the derivatives that you can get from your calculator on here. And then, what are going to be our critical numbers here? Well, can f prime of x equal 0? No. Can it be undefined? Can x squared plus 2 to 3 halves equal 0? No, because any x squared plus 2, there's always going to be positive. This is raised to 3 has power. It can't be 0. So no. Now over here, though, f double prime of x could equal 0, because negative 6x could equal 0, the numerator. So we get that x equals 0. So this becomes our key idea here. X equals 0. It's not a possible maximum min, but it is a possible inflection point. And when you put 0 back in the original function, you get 1 over square root of 2. I'm sorry, you put in the original function, you get that. Its slope is 1 over square root of 2. We called it a critical number because it had 0 for the second derivative. And now we just check the sign of the second derivative on either side of 0. So put any positive number in here, you see you're going to have negative over positive, so that's negative. So when x is greater than 0, you're going to have a negative second derivative. When x is less than 0, you put a negative number in here, that'll cancel the negative there. All this will be positive. So you'll have a positive second derivative to the left of 0. So that means the concavity changes. This is key. A positive second derivative means it's concave up. A negative second derivative means it's concave down. And so that's why in the graph, since we have a change in concavity, this will be an inflection point. Now, the horizontal asymptotes are from that tricky process we talked about before when you have a radical underneath. And these are something you can discover too by just putting your calculator and checking out the graph. But this is one of the key points to plot here is this inflection point. And also again that horizontal asymptote. Here's another radical function. Here it's easy enough to do the derivatives because you can just use the power rule here, bring the 5/3 down so you get 10/3 x to the subtract 1 from this and you get 2/3 minus bring the 4/3 down, you get 20/3 x to the 1/3. So you got our first derivative there. And the second derivative, bring the 2/3 down, you get 20/9 x to the negative 1/3 minus 20/9 x to the negative 2/3. And so now because we have negative powers, this can be thought of as 20/9 x to the 1/3 minus 20/9 x to the 2/3. And so we're going to find at x equals 0, our second derivative becomes undefined. So that's something we're going to have to look at as a possible inflection point. Can the first original function, can the derivative equal 0? Let's take a look at that. If we set f prime of x equal to 0, we get 10/3 x to the 2/3 minus 20/3 x to the 1/3 equal to 0. We're not going to be able to make this undefined because we're not dividing by x at all. I'm going to multiply through by 3, 10x to the 2/3, and put the 20 on the other side. Maybe divide both sides by x to the... Actually, I'm going to look at it this way. I'm going to put it back over here again and say x to the 2/3 minus 2x to the 1/3 equals 0. And actually factor out x to the 1/3, leaving x to the 1/3 minus 2 equals 0. Because this x to the 1/3 equals 0 will give us one possible critical number, x equals 0. And x to the 1/3 equals 2 gives us another one. We cube both sides, and we get x equals 8. So we got 0 and 8 for possible critical numbers there. There's our derivatives. And some of the critical numbers we want to look at are 0 and 8. Now, why do they throw in 1? Let's take a look again here. X to the 1/3, it's where the first function is. Hold it. Here we go. The second derivative will be undefined at x equals 0 now, but we also get, in this factored form for the second derivative, we can see that we can set the second derivative equal to 0. That means we'll set the numerator equal to 0. And so x to the 1/3 equals 1. Cube both sides and you get x equals 1. So there's another critical number for you. So 0, 1, and 8, and we're checking this stuff in between. Now, my big question is, was this negative 3 a point of inflection? You've got a 0 second derivative. And notice we test the second derivative on either side of this x equals 1. And between 0 and 1, if you put a number between 0 and 1 here, it gets negative. If you put a number between 1 and 8 in here, it's positive. So this means that it went from concave up to concave down to concave up, so you must have an inflection point there. So that's one of the key points there. Notice at x equals 0, where the derivative was 0, but the second derivative is undefined, we can't use the second derivative test there. So you'd be forced to use the first derivative test and look at the fact that the derivative changes sign from positive to negative. So if the first derivative is positive, that means the function is increasing. First derivative is negative, it's decreasing. If it goes from increasing to decreasing, just has a relative max there. Okay? At 0, 0. Okay. Now, polynomial functions. These work out a lot cleaner and they're a lot easier to do the derivatives and so forth because you can just take f prime of x equals 4x cubed minus 36x squared plus 96x minus 64. Looks like 4 goes into everything there. So we can factor out of 4 times x cubed minus 9x squared plus 9, 6, and 4, 24x minus 16. Now you set that equal to 0, so we can start looking for some critical numbers. And this is one thing where I might go to Poly. I hope you've got Poly in your apps menu. Under apps, it's polynomial equation solver. And you just put in the coefficients really quick and you come up with your roots. You got to tell Poly the degree. In this case, the degree is 3rd degree. And then you just got to put in the coefficients, and we can go to the original coefficients or these, either way. I'm going to put in the original 4, negative 36, 96, and negative 64. And solve. And solve. Now, Poly did something strange here. It gave me x equals 1. And then you got to watch out because it gave me these other roots that look like 4 plus or minus 0.00009134i. Well, you got to know that that's probably a round off error by it. And let's just verify that, because I'm thinking I'm getting 4 as a double root. And sometimes Poly will do that with double roots. Let's check it out. If we put in 1, negative 9, 24, negative 16. 1, negative 8, 16, 16, 0. Sure enough, it works. And this x squared minus 8x plus 16, sure enough, is x minus 4 quantity squared equals 0. And that's where we get our x equals 4 twice. So we get x equals 0 and we get x equals 4. Now let's also investigate the second derivative. And the second derivative, just branching off of this one, is 12x squared minus 72x plus 96. Okay, and I believe that when you can factor out a 12, leave mind x squared minus 6x, and 96 divided by 12 is 8. Plus 8, and that factors nicely into x minus 2 times x minus 4. So then we get 2 as another number we want to look at. Now here the book suggests a factoring thing if you saw that. When you factor out the x, you saw the rest was x minus 4 cubed. Now you can go about using the product rule on the factoring. Well, the trick is, did you see that that was x minus 4 kind of cubed? Maybe you could have by doing the factor on the calculator. Okay, so our first and second derivative then yields our possible critical numbers. The first derivative set equal to 0 gives us 1 and 4. Possible points of inflection at 2 and 4. Our end behavior. The x and y intercepts you can get from that factored form. 4 and 0. And so there's the critical numbers of 1 and 4, and we also look at 2. And to judge relative max and mins, you can use the second derivative test here. See where the first derivative is 0. The second derivative here was positive. That means it's concave up, so it's relative min. Here at x equals 4, the second derivative is 0, so it's inconclusive. But this is x equals 4 also made the second derivative equal to 0, so it's a possible inflection point. And since the second derivative changed sign, we do have a point of inflection there. We also get one here as well. And let's see what this looks like. There's a point of inflection there, and here, and just a relative min. Notice no relative max. Oh, I'm sorry, it was a 4th degree polynomial originally. I was looking at the other one. So the end behavior, let's look back at that end behavior again. Yeah, as you approach in negative infinity and positive infinity, the y's are going to approach positive infinity since it's a 4th degree. Okay. A polynomial function E in green must have at least one relative extrema because it has to turn around and go to the other infinity. All right. That's enough for now. Flange out.